So welcome to another session of Design and Analysis of Algorithms course. So in this session, we'll be talking about fundamentals of algorithms analysis. What is meant by analysis of algorithms? The term analysis of algorithms is usually used to mean an investigation of an algorithm's efficiency or complexity with respect to two resources. That's the running time and the memory space. So running time tells you how much time the algorithm takes to complete its task. And the memory space analysis tells you how much extra space the algorithm takes to perform its action. Though we talk about running time and memory space, most often we focus on computational time because that's most critical in many cases. Often the difference between memory space requirements of two algorithms is not that significant, except in certain specific cases. So that's why we focus more on computational time. So it's clear that the algorithms take longer on larger inputs. For example, if you take the case of a sorting algorithm, the time taken by the sorting algorithm depends on the number of elements to be sorted. If the number of elements is larger, obviously the algorithm will take more time. Hence, we always investigate an algorithm's efficiency as a function of its input size. We try to create a function, express the algorithm's complexity or efficiency as a function of its input size, often represented as n. Now, choosing an appropriate input size is important. So, what you consider as input? So, in the case of sorting algorithm, number of elements to be sorted is its size. In the case of graph algorithms, it could be the number of vertices, or it could be the number of edges, or a combination of both. The algorithms that operate on matrices might use the number of rows, number of columns, or number of elements as its input, right? So the complexity analysis will consider those numbers as the size. A spell checking algorithm may take number of characters or number of words as its input size. Now, how do we analyze the running time of an algorithm? How do we find the running time of an algorithm? There are two approaches possible. The first one is implement the algorithm and study its running time by executing it. When you execute it, you would have to test with various inputs, and you might plot how the time varies with respect to the input size. When the input is increased, how much the running time varies, etc. So this involves recording the actual time spent in each execution. But there are many challenges in this particular approach. The first one is, in order to measure the running time, you have to first implement the algorithm. The second one is, it's often difficult to accurately measure the time taken by the specific algorithm. So when you run an algorithm on a computer, it's possible that there are other programs running on it. How do you isolate the time taken by this specific algorithm? So one obvious way we can do is, don't run any other program in the computer. But then there are operating system processes which always run. So that's the challenge. The third difficulty is how do we measure two algorithms? When we measure two algorithms, we have to ensure that both of them are run on the same hardware environment, because one machine may run faster, the other may run slower. So in order to make a meaningful comparison, we have to execute them on the same hardware. We also have to execute the program with various inputs. Our objective is to find out how the algorithm's running time varies, or how they estimate the running time as a function of its input size. So we have to try with various input sizes. And later we will also see that it's not just the input size, it is also the uh, configuration of the input that determines it's not just the input size, but also the configuration of the input, or the order in which the inputs are arranged also matters. So we have to try with various input organizations, various input sizes. So all these poses challenges. So this forces us to look for an alternate way of analyzing the running time. And that alternate approach, or the second approach, is based on an analytical framework. So in this framework, we don't measure the running time in terms of seconds, but we measure we count the number of times each of algorithm's operation is executed. How many times each operation is executed, count the total number, and express the running time as a function of this count. But this is excessively difficult, especially if the program is very large. We have to look at how many times each operation is performed, and that can become very complex. And we will also see that this is not really necessary. We don't need to really count the exact number. We can go for some approximations. So what we do is we identify the most critical operation in the computer, the most critical operation in the algorithm, and count the number of times that critical operation or the basic operation is performed. For example, in the case of a uh, sorting algorithm, which involves two for loops, the critical part of the algorithm is the operations performed inside the inside loop, because that's the set of operations uh, that will be executed most. So we count how many times the operations on the inner loop are executed. So we express the running time as a function of this count, or this count is also a function of the input size n. Now this analytical framework allows us to evaluate the relative efficiency of two algorithms without executing. That means we don't have to worry about the hardware, we don't have to worry about the software environment. We can do the analysis without the hardware and software environments. Now we make certain assumptions when we do this. We use a model called the random access machine model, where we assume that we use a single processor. Instructions are executed one after another. So we assume that there are no concurrent operations. When, and also we assume that each basic operation takes same amount of time, whether it's adding two integers or multiplying two floating point numbers, or a statement which involves addition plus multiplication. We assume that all of them take constant amount of time, though multiplication of two floating point numbers takes significantly larger time compared to addition of two integers. But we make a simplification there. We assume that each basic operation takes same amount of time. That's a simplification we make. And since we are making that simplification, the analysis framework often ignores the multiplicative constants. That is, let's take this example. Let's say there are two algorithms. The first one performs 2 multiplied by n square basic operations, and the second algorithm performs 10 multiplied by n square basic operations. And if these algorithms are, sorting algorithms, it's possible that the inner loop of the first algorithm has two operations, the inner loop of the second algorithm has 10 operations. That's how we arrived at these numbers. But since we are ignoring these multiplicative constants, we say that both of these algorithms have the same complexity. Both of these algorithms have complexity of n squared, and we uh, specify that using the big O notation as big O of n squared. We will look at the different notations like big O, small o, big theta, etc. at a later point of time. So, so since we are not really worried about the multiplicative constants, uh, and uh, we normally are not really worried about the algorithm's efficiency for small numbers. The running time uh, varies significantly when the input size becomes enormously large. For example, if you take two algorithms, the first one performs 200 yen, and the second algorithm takes 2 n squared operations. For a small size of n equal to 10, the first algorithm takes 2000 basic operations, whereas the second algorithm takes just 200 basic operations. For small size input, the first algorithm takes more time. Whereas if you look at a uh, value of n equal to 10 to the power 6, that is 1 million, the first algorithm takes just 200 million, whereas the second algorithm takes 2 million operations, which is significantly higher than the first one. So hence for larger outputs, we don't prefer an algorithm which runs in n square time. We prefer a linear time algorithm. Whereas for small inputs, it doesn't really matter. Uh, this is a table which indicates how the running time increases as a function of n. So there are seven different categories of algorithms given. The first category of algorithms takes log n to the base 2 operations. The second one is proportional to n, like for example a linear search, etc. The third one, n log n to the base 2, and the fourth class of algorithms takes n square, where n is the input size. The fifth one takes n cube, and so on. Now we can see that for a small size of n, it varies from 3.3 to 10 to the power 3 for polynomial functions. But when it becomes exponential function, 2 to the power n takes 10 to the power 3, and n factorial takes 10 to the power 6. But even for a small value of 100, the exponential algorithms take significantly larger amount of time. For example, 2 to the power n takes 10 to the power 30 amount of time, which is very large. Even on a in the present day computers, it takes years together to perform that computation. And it's clear that for any size larger than 100, exponential time algorithms won't work. And for polynomial time algorithms like n, n squared, n cube, etc., for a value of 10 to the power 6, log n takes just 20 operations, whereas n cube takes 10 to the power 18. So you can see there is a significant difference in the time taken when the input size becomes very large. And that's what we are interested. So we are really interested in how the running time grows when the input size grows. That's what we focus on when we talk about analysis of algorithms. Okay, now the let's talk about the worst case, best case, and average case efficiencies. The running time of many algorithms depends not only on an input size, but also on the specifics of a particular input. We'll explain, we will look at that with a specific example. Let's take an algorithm which does a sequential search. So what does this algorithm do? You are given an array of size n and a key value k. So this algorithm has to find whether the key k is present in the array or not. If the key is present in the array, it returns the index position at which the key is present. If the key is not present in the array, it returns a value of -1. That's what this algorithm does. And the algorithm implementation is very simple. So you start a counter I, which indicates the index position. You initialize it to 0, and then you run a while loop. If we keep on checking the uh, element at each index position and see whether the key value matches that index position or not. And if it doesn't match, you keep on iterating over the array and you continue that until I becomes n. So as long as I is less than n and you have not found the key value, you keep on incrementing I value, the index value. And you come out of the while loop if I becomes n or if you find the key value. So if once you come out of the while loop, if the value of I is less than n, it indicates that you have come out of the while loop since you have found the key. Okay. So in that case, it returns the value of I. If if the value of I is equal to n, it indicates that you couldn't find the key in the array because you have gone beyond the array. Hence, it returns a value of -1. Now let's try to understand how many times each of these operations are performed. I mean, it depends on the key value and also the elements in the array. Let's take the case where the key is present as the first element in the array. So if key k is present as the first element in the array, the while loop is executed. The while loop condition is checked and it comes out of the while loop because the condition ai not equal to k is not satisfied, so it comes out of the while loop. So in this case, you can see that the entire number of operations performed by the algorithm is a few operations. It does not depend on the value of n. Irrespective of the number of elements in the array, the while loop is executed just once, only the checking is done, and the return value is performed. But let's take the other case where the key value is not present in the array. If the key value is not present in the array, we have to search the entire array. That means the while loop is executed n times. Hence, the number of operations performed in this case, that is case where the key is not present in the array, is n. So the number of operations performed varies from a few constant operations to n. So we say that in the best case, that is, the key is found as the first element, the complexity is a constant. In the worst case, that means the element is not present in the array. That's the worst case. The number of operations performed is n. So we can see that the number of times these operations are performed depends on the key value k and whether the key is present in the array and at what location the key is present. So it's clear that the running time of this algorithm does not just depend on the input size, but it also depends on the specifics of the input. So the best case is k is the first element in the array, and the worst case is k is not present in the array. So let's do a formal definition of worst case, best case, and average case. The worst case efficiency of an algorithm is its efficiency for the worst case input of size n. So that's an input for which the algorithm runs the longest among all possible inputs of that size. So we have seen that in the previous example, the worst case is when the key is not present in the array. The best case efficiency of an algorithm is its efficiency for the best case. That is, the least number of times the algorithm runs on a particular input, or the fastest the algorithm runs on all possible inputs of that size. Okay, so we have seen that in the previous case, for an input of size n, the algorithm performs a constant number of operations if the key is the first element in the array. Now, the third category of analysis is the average case efficiency analysis, and this is much more complex. The average case efficiency of an algorithm is its efficiency on a typical or a random input. So in our case, if you assume that the key is present, the key could be the first element, it could be the second element, it could be the third element, or it could be the last element. So on an average, you have to scan half of the array, assuming that the key is present. So you can say that the average case is half of n. But then there is another complexity. What happens if the key is not present in the array? Obviously, it takes n. And how many times or what is the probability that the key is not present in the array? So the probability also plays into account when we talk about average case efficiency. So often we don't focus on the average case efficiency in most cases. We talk about worst case, best case, average case. In certain cases is not very difficult to compute, but in many cases the average case is not easy to compute. And when we express the efficiency of an algorithm, generally we specify the worst case efficiency. So unless explicitly stated otherwise, when somebody says the complexity of a sorting algorithm is n squared, we are saying that it is a worst case efficiency or worst case complexity. So in this algorithm's case, the worst case complexity is big O of n, the best case is big O of 1. We ignore the constants. And the average case also is big O of n, because even if you assume that it's a 0.5n or 0.7n, depending on the probabilities, we ignore the constant and we say that the average case is big O of n. Okay. Now let me summarize what we have learned about the analysis framework. So we normally measure the time and space efficiency or time and space complexity of algorithms, and both of these are measured as functions of algorithms input size. The time efficiency is measured by counting the number of times the algorithm's basic operation is executed. Space efficiency is measured by counting the number of extra memory units consumed by the algorithm. The efficiencies of some algorithms may differ significantly for inputs of same size, depending on the configuration of the input. For such algorithms, we need to distinguish between the worst case, average case, and best case efficiencies. And the analysis framework primarily focuses on the order of growth of the algorithm's running time as its input size grows to infinity. So we generally worry about the running time when the input size becomes significantly large. So before I wind up, I will give you two exercises to work on. The first one is outline an algorithm to find maximum of n elements and obtain its complexity. So let's say you are given an array and you have to find out what is the maximum, the value of the element that has the maximum value. Okay, you have to find that. You have done this algorithm probably in your programming codes or data structures course. But what you have to do is write the algorithm and do an analysis in terms of its time complexity. The second algorithm is to design an algorithm for checking whether all elements in a given array are distinct or not. So you have to find out whether there are duplicate elements in the array or not. Now the second algorithm has different implementations possible, and these algorithms have different running times, and in certain cases you can achieve a faster running time at the cost of using extra memory. We will discuss the solutions for these algorithms in the next class. So I suggest you to work on these problems and come to your own solutions so that you can appreciate uh, the solutions when I discuss them in the next class. So I'll stop here.